In this video, let's talk about 4.1 linear momentum. In Unit 4 of AP Physics 1, linear momentum. So, let's talk about some of the concepts that you'll encounter. So, momentum is inertia in motion. So what this means is that it is a measure of how hard it is to stop a moving object. And it is used in collision problems. Now let's talk about how it is a vector. So this means that the direction matters. Because positive, negative must be consistent with chosen axes. So don't make any sign errors. Okay, so also, momentum changes only because of net external impulse. So this means that internal forces, for example, between colliding objects, cancel out. So only external forces change the final momentum. Next is that, so this is conservation of momentum. Now let's move on to how momentum relates force to time. So what this means is that force applied over a time interval creates impulse. And this changes momentum. So this relates back to the impulse momentum theorem. So let's talk about some critical formulas that you have to know for this subtopic. So what is momentum? Remember that momentum is the vector of p is equal to mass times the vector of velocity. You need to include the direction, and remember that this is measured in kilograms times meters per second. Now let's talk about the total momentum of a system. So P total is going to be equal to the summation of MI, VI, And also for two object systems specifically, here's the formula. So it's going to be P total is going to be equal to mi vi plus m2 v2. Now let's talk about momentum as a function of time. So let's talk about pt is equal to m vector v times t. So what it's saying is that if velocity changes with time, so for example, an accelerating object, so does momentum. Now let's talk about the momentum and force relationship. So the summation of the F forces is equal to dP divided by dt. And specifically, if mass is constant, then we can simplify this further to the summation of F is equal to m times dv over dt is just simply equal to ma. So essentially Newton's second law. Now here are some things, some more critical facts that you need to know. Some core facts include the fact that, again, momentum is a vector, so you need to track the signs. Only external, okay, let's write that up here. Only external momentum is a vector. Pay attention to the fact that only external forces change, and internal forces, they all cancel. And remember, let's add to this list over here. Yeah, so internal forces, this is due to Newton's third law, equal and opposite, and the net force, the external forces. This means that without external forces, momentum is conserved. Again. So also remember that for collision problems, that inelastic, and also in explosions, momentum is conserved. And also, another thing that you really have to remember is that the direction of velocity will tell you the direction of momentum. Since when you multiply together the things to get the formula for momentum, mass times velocity, only velocity is the only vector. And again, as we know, mass is always a scalar, so you will just transfer you only pay attention to the vectors, positive or negative sign. And remember that, again, momentum is going to be in kilograms times meters per second. Mass is always going, mass is just in kilograms vector, velocity, sorry. And let's write these on here. Impulse is going to be newtons times seconds, kilograms times meters per second. And force, remember, is going to be newtons equals to kilograms times meters divided by seconds squared. Okay, let's create a connection table that will connect momentum versus velocity versus mass. So let's say that we increase m, and then let's say we hold v constant. That means that momentum p will increase because heavy objects have more impact at the same velocity. So for example, that's why trucks cause more damage than cars. Now, let's say that we increase v and then we hold m constant. That means that the total momentum will also increase. And the reason for this is because faster objects is harder to stop. So, for example, think about sports and also driving. Let's say that we double v and we double m. This will mean that p will increase 4 times. This is because momentum scales multiplicatively. Okay, let's talk about momentum as a vector. So let's talk about the signage on momentum for a moment. Move this over here. So a positive momentum. So if p is positive, this means that this means right. If p is okay, so remember that if if your vector is positive, that means that it's gonna go to the right, you know, and if it's negative, it goes to the left, and that affects the signage on on your momentum. Okay, so let's talk about internal versus external forces down here. Internal, external force. So internal means that, you know, object A pushes B, and this means that momentum is canceled out, it's canceled by Newton's third law, okay? And it doesn't change the system momentum. But let's take, for example, external forces. Like, for example, friction, the wall, and also the ground. This actually changes the system. This actually changes the system momentum because it's being added to the system. Add or removed from system, from the total. And remember that the system must be isolated. in order to use conservation principle. Okay, let's move on to when is momentum conserved or not in the following scenarios? Is momentum conserved? Well, let's work this out together. If, let's say we have two carts sliding on a frictionless track. In this yes, P is conserved. The reason why is because there are no external horizontal forces. Now, let's say we have a gun firing a bullet. Well, if we have a gun firing a bullet, yes, that's because we can define the system as the gun plus the bullet. And that means that there are internal forces only. So you basically just think about it as like energy being transferred inside of the system. Therefore, the momentum is still the same inside of the system. So let's say we have an object hitting the wall. If you have an object hitting the wall, then momentum is not conserved because the wall exerts an external force onto the system. And yeah, so that does not conserve momentum. So let's say we have a person jumping off the ground. Well, if you have a person jumping off the ground, the momentum is not conserved because the system is gonna be the person only. And that means that the ground gives external impulse. Let's add this over here. Okay, so let's talk about some critical formulas for momentum. Again. So yeah, let's just add that up to here. So again, we had this total momentum of the system, two objects in the system, this, yeah. Okay, so remember that this is the fundamental quantity of the entire unit is this P equals mv. You need to know this. Well, you should already know it. And let's remember these key facts. If V is equal to 0, then P is equal to 0. Also, remember that if M does not equal 0 and V changes direction, that means P also changes direction. Okay, that means that P also changes direction. Okay, let's say that if mass changes, which is usually not tested, then P will change even. P changes even with constant V. Okay, so back to the total momentum of a system. Remember this. Well, let's say, for example, we have 2 carts on a track. This is actually meant for this one. So let's say we have P initial is equal to MA, VA is equal to plus MB, where A and B are like carts. Okay, so let's talk about, again, momentum and force relationship. So for this, if the sum of the forces is equal to 0, then you know that the momentum is constant, because there are no net forces. It's equal to 0. So you can interpret this as like a big a big force for a short time. This is gonna mean that there's gonna be a big momentum change. But let's say that there is a small force for a long time. This is still going to be a big momentum change. The reason why is because, you're kind of compensating for it by increasing the other variable, Okay. Also, let's say that if net force is equal to 0, momentum is constant, but it is not necessarily equal to 0. Okay, so let's continue. Remember that, again, like momentum is conserved in all collisions. Okay, but kinetic energy is only conserved in elastic collisions. Now let's remember that let's calculate let's do some examples actually. Let's say that a 2 kilogram cart goes right at 3 meters per second. So that's just really simple. MV, 2 times 3 is just equal to 6 kilograms per second. Let's do a problem with opposite directions. Okay. Let's say that we have, so let's say that cart A is 3 kilograms and it's going positive 2 meters per second. And let's say that cart B is 1 kilogram and it's going negative 5 meters per second. So what is the total momentum? So the total momentum is just going to be 3 times 2. And then 1 times negative 5. And that's literally just equal to 1 kilogram. 1 kilogram meters per second. So let's say for a third example, let's say this is a problem about 0 net force, which means that momentum is constant. So in this scenario, let's say we have a puck glides on ice, which means that it's frictionless. And that means that since the summation of F is the summation of the forces is equal to 0, that means that dP divided by dt is going to be equal to 0. Therefore, you know that that means the momentum is going to be constant, not necessarily 0, but like regardless of motion, you know that it will stay constant. Okay, now that's about it for